Good afternoon, guys. The following is the first part of the video lecture on chapter 4, motion in 2 dimensions. The idea with this chapter is to continue the study of motion, but now focusing on 2 dimensions, of course, 2 dimensions, right? So the main, one of the main goals is to study projectile motion. That's up until what I want to get today. All right. In the next video, I will do more problems on circular motion. Now, as you know already, we have position and displacement, right? That can be described as a vector, as you have in there. But now, we don't say delta x or x as a vector, or just unit vector I. We call position vector R, or delta R for R final minus R initial. And the reason why we do that is because R, if you remember from the first chapter on vectors, is the magnitude of the resultant of a vector with 2 components, X and Y. So it's important that you remember that, right? So we can actually, from that base, we can define the velocity vector, which is now the variation of R as a function of time, respect of time. And remember, right, delta R over delta T will be the average velocity. But then, of course, we define the instantaneous velocity, which is a velocity at some point in the trajectory. For that, we take the limit as delta t approaches 0, and that becomes the derivative of position respect of time, right? That actually is a general equation, right? And in fact, we can use R as a position vector for a vector in 3 dimensions, right? X, Y, and Z. So now you are looking at a more general description of displacement, position, and velocity. All right. And of course, as you can see there, you can have a curve in the X and Y. Now it's not position and time. Now we're looking at the position X, position Y. Right? So they both can change as a function of time. Remember that the velocity or the speed is the magnitude of the velocity. That's important there. So what about acceleration? So we know that in 1 dimension, acceleration can be or can happen due to the change on velocity respect of time. So dv dt or delta v over delta t. If you're looking at the average acceleration. However, what you see there, what you are seeing right now in there is 2 different positions along a curve here. And as you know already, the tangent line at certain positions of the curve give you the velocity because the slope of the tangent is a derivative. That's calculus 1. If you guys have questions about that, please let me know, and then I can go more in depth in a office hours meeting. All right. But here, basically, you have the tangent line and the slope will give you the velocity, and that's why we mark it here. And the same here. But the velocity is changing. Why is the velocity changing? Because the magnitude is changing. You see the magnitude of these vectors is different. So if there is a different magnitude, a different velocity, then there is a change of velocity. And that happens in a period of time. So then there is acceleration. So why is there acceleration if actually, let me stand corrected. The magnitude of the velocity is not changing. What's changing is the direction of the velocity, which therefore gives you a different value for the velocity. 4i is not the same as 4j, right? If we draw 2 vectors even though the magnitudes may be the same in the X and Y axis, I can write a horizontal V there, and that V has only the X direction. Here I can write, they both have the same V. But this is now on the negative Y direction. This in the positive, right, unit vector I. So even though their magnitudes are the same, they are not the same vector. Therefore, we have a change on velocity. And that is what? That is a definition of the average acceleration. So you can have acceleration when there is a change on the direction of motion. We will see that more in circular motion, by the way. But just in case, so you can see it. What is instantaneous acceleration is the first derivative of v respect of time. It's the same as how we define here the instantaneous speed. So that's a review of what we did before. And in this question, what needs to change when you are driving to cause an acceleration? You have to slow down, accelerate, or change direction. So any of these will cause an acceleration. So all of the free controls in a car, and you probably experiment this every day. When you do a turn, you either slow down and if you're not slowing down properly, you can actually crash. That's why you have to be careful when you turn, because there is acceleration happening, even though it's not very noticeable. In some cases it is though. So that is the first simple form that we're going to be studying. Two-dimensional motion with constant acceleration. So a particle or an object moving in the X and Y plane. And just as I said before, X and Y are the components of the vector position R. So how can we write R then? R is a vector, and the two components are X and Y. Y is in the J direction, X is in the I direction. Remember, guys, I is the unit vector for the x-axis, J is the unit vector for the y-axis. So I can write R in vector form as xi plus yj. And then I can get all my definitions for velocity and acceleration using this, because I can do delta R over delta t, or the first derivative of R respect of time, and the derivative is applied on each unit in each component. So you are seeing the velocity on X and the velocity on Y. And then I can do a second derivative and I find the acceleration. Now, we have acceleration on X and acceleration on Y. So you can have different positions in X and Y due to different velocities and different values of acceleration. What you're seeing there is the general expression for the final velocity on respect of time in X and Y. Right? The velocity here, initial, and the acceleration. You will understand this more when we do problems. And that was the general equation that we did, right? When there is, remember guys, this is when there is constant acceleration. It's not always the case. For example, I can give you the position respect of time of a particle moving in a very random trajectory, not necessarily a line or a parabola. And then we can apply calculus to find the velocity and acceleration as a function of time. Right? And you remember that the same formulas for constant acceleration can be applied in both. It's going to be very important when we do projectile motion, by the way. And there it is. Right? There's no problem. particle moves in the XY plane starting from the origin at t equals to 0. T equals to 0. With an initial velocity having an x component of 20 and a y component of minus 15 meters per second. The particle experiences an acceleration in the x direction given by 4 meters per second squared. So we're going to find several values or parameters as a function of that. So let's draw this problem on the board. So 20x minus 15y. Okay. So we are going to draw these vectors. The particle starts on the origin. This is my x. This is my y. And it has 20 on the positive x-axis. And negative 15, I draw it like this. But there is an acceleration of 5, right? 5 meters per second square, 4 meters per second square, sorry. On the x-axis. So the nice thing is that we can actually use the equations that we derived before, but now in general, R equals to R initial. Actually, we want the velocity, right? So V final equals to V initial plus acceleration time. You know, I'm gonna give you a strategy, guys. Break it into components. In fact, when we do projectile motion, you will see that that's more useful. So I can do first on x, when there is acceleration. V final on x is equal to V initial plus acceleration on x. V final on y is still negative 15 meters per second on the y direction, and this will be meters per second on the x direction. That's what you want to write. And then you can evaluate for some given time, right? What will be the velocity? That's what they ask you in the second question, right? Actually, they're asking you, well, you want to write it in vector form. So the velocity is parentheses 20 plus 4ti minus 15j meters per second. That's the velocity. And then obviously they can make you calculate the velocity for t equals to 5. So we're going to find the vector velocity and then the magnitude at t equals to 5. What you do is you evaluate on 5. V on 520 plus 40i minus 15j meters per second. That's vector though. How do you find the scalar? I take the magnitude, which is the square root of 40 squared plus negative 15 squared. And that gives me approximately 43 meters per second. So magnitude and vector, right? What other information can I get from this problem? So what I can see is that after some time, the particle is probably going to be moving like this, right? That's the trajectory. After 5 seconds, I can find the angle or as the particle is moving, in which angle respect to the x-axis, right? At t equals to 5, I can find, well, this is Vx, this is Vy. I can find this angle. How do I find that angle? This is space here. To find the angle theta, you say that tangent of theta is equal to Vy or V final on Y over V final on X, or Vy over Vx, that's fine. And I have Vy Vx is minus 15 over 40. So theta will be the tangent inverse of negative 15 over 40. And what is that? You go into the calculator and we find that it's approximately negative 21 degrees. So we get negative 21 degrees. Yeah, we're here. All right. Then later they ask you to find the x and y coordinates as a function of time. Okay. Because the acceleration is constant, I don't have to use the integral, right? Because technically, if the acceleration was not constant, guys, you would have to integrate because this will be dx dt, dy dt, right? Actually, you could integrate. Yeah, you could integrate. So I want to give you both ways, all right? But remember that you can always use calculus if you're comfortable with it, all right? So I'm going to leave this in here, and let's find the position on x and on y. So we're going to find the r vector, finally. And the thing is, calculus is a very important tool for math, for physics. Physics 1, physics 2, right? So we know that x as a function of time is x initial plus v initial on x times time plus 1/2 acceleration on x t squared. Right? Make sure that you guys are seeing that. Yeah. And the same I can say for y. But for y, there is no acceleration. So it's just y initial plus v on y times time. So for y, as a function of time, will be minus 15 t j meters. For x, because the initial position was 0, right? So this is 0, the origin. We just write this. The initial times time plus 1/2 of acceleration plus 2t squared. So what will be my position? R will be this guy minus, let's put here minus 15t j meters. All right. How will I use calculus for this? So for this part, let's show you this guy. I have to put this in here. Bfy or B on X is that. But what's B on X? So I did this in the previous chapter. Now we have 2 dimensions. I integrate this, I get 20t plus 1/2 x minus x initial, which is 0, x. There. Right? So that's 2 dimensions. I mean, it's a very generic type of problem for 2 dimensions. Let's focus now on projectile motion. Let me just see here. Yeah. Okay. So projectile motion is a particular situation for motion in 2 dimensions. I mean, within projectile motion, there is a very simplistic scenario. I'm going to do a general one first. I will derive the equations, I will show you the particular situation, and I will finish the lecture here. Next class, I will do a couple of problems on that, next video, and then I will start with circular motion. All right? Maybe there will be 3 videos for this chapter because circular motion can be a bit long. All right? Because you have acceleration and all that, but at least projectile motion, you will be, it will be done right now. Let's erase all this. And let's show you guys projectile motion, which is a particular situation on motion on 2 directions. Okay. Here. All right. As the name says, we are now going to deal with projectiles being launched. And the most simplistic scenario is when you have a rocket or a football that is being launched with some initial speed v at some angle theta, and the trajectory will be given by this. So another name for this is the parabolic motion, by the way. So for projectile motion, we are going to assume the following: that on X, so in the horizontal, there is no acceleration. On y, we want to say that there is just gravity. So there is acceleration. Gravity is affecting it, right? It's making it go, it's making it slow down and then go down. So we should put here gravity. So what you have here, guys, is a combination of uniform motion on the horizontal and free fall on the vertical. The thing is that the best way to approach these problems is by breaking this velocity into components by using the angle theta. So that's the first step. You are gonna find the velocity in two components. That's that. And then you have on the horizontal and the vertical. Vy, Vx. But actually, Vx initial, Vy initial. But on x there is no acceleration, so just put Vx. So what is Vx? V cosine theta, that's vectors. And what's Vy initial? V sine theta. Very important equations, these ones. That's how you break into components. So, two dimensions, right? X and Y. Let's write down here X as a function of time. Without assuming that you are using the origin, you can say that the position as a function of time is the initial position plus the velocity of x times time, change in time. And if I want to use this guy, I will say that x as a function of time is x initial plus V cosine theta delta t. Furthermore, if the initial position was 0, you start from the origin, and then you get you will get that. You can even say the range, the horizontal distance traveled. But for now, we will say the position as a function of time. No, initial position will be B cosine theta. So we found our first equation. What about on y? On y, what you guys have is just an object going up and then going down. So there are a few things we can get. I just got the range of the projectile. This equation here gives me the range of the projectile. All this is x, by the way. Right? X. That's the range. For the vertical motion, you have a few parameters, but one of the main parameters is the maximum height. Let's call this H max, which you know is in the vertical, so we're gonna find delta y. On y, delta y is the initial y times delta t plus 1/2 gravity squared. but we know gravity goes down. So to find the maximum height, you say that the maximum height is V initial on y, delta t, minus 9.8 t squared. It's a quadratic equation. Negative quadratic, that's why it's a parabola opening down. But that's the equation. In fact, you can even put here delta y. Let's not talk about H max yet. Delta y. What do we know about the maximum height? We know that at the maximum height, the final speed on y is 0. So then I use this equation. V final on y squared equals to V initial on y squared plus gravity time. Sorry, what I'm talking about. Plus 2 times gravity times delta y, which will be now H max. I know that my V final is 0, so my maximum height is no other than the initial speed on y squared over twice the value of gravity. Why positive? Because this will become negative, right? Due to this negative gravity. So that's the equation for maximum height. And what's Vy initial? Is V sine. So I have here V squared sine square of theta over 2g. Guys, you don't memorize the formulas. You want to understand them and use them. So I found the range and the maximum height. But what else can I find? Right? What other things can I find? I can find for how long was the projectile in the air. And to know that, you only need to know how long it takes to go up. Because by symmetry, the time to go up is equal to the time to go down. We did that also in falling objects, right? The time to go up is the same as the time to go down. So we multiply by 2 the time to go up. So I can actually use the definition of acceleration of gravity in this case. I erase this now. I can say again on y, going up on y, the final speed on y is 0. Maximum height, that's the time to go up. That's when it goes up. So the final speed on y equals to the initial speed on y plus gravity, the time to go up. That's negative because of gravity. This is 0. So then I get that the time to go up is equal to this divided by gravity. And what's this? V sine theta over g. But that's only the time to go up. The total time is 2v sine theta over gravity. So I have the flying time. What other things can I get? Well, to find the range of the projectile, I need the total time it takes to go from this point to that point. So what is this delta t here? That delta t is the flying time. So I can write It's right over there. Actually here. Let's see, where is this? So we know already that the range of the projectile x is equal to v cosine theta times the total time. But the total time is this. So this will be v sine theta parenthesis 2v sine theta over gravity, v times v, v squared. 2 sine cosine is what? Sine of 2 theta divided by gravity. Actually, guys, you know why I'm showing you this equation? Because many of you have heard that the maximum range for a projectile is when you have an angle of 45 degrees. Well, we can prove it now. Here. How do we prove that the maximum range for a projectile is when the angle is 45? Actually, as a function of theta now, right? There are two ways you can think about it. Sine of any angle, so sine of x or sine of c, you get confused with that, is always greater than -1 than 1. So the maximum value of sine is when it's 1. So c has to be 90 degrees, pi over 2. So if 2 theta is pi over 2, that's when you have the maximum range. How much is theta? Pi over 4. What's pi over 4? 45 degrees. That's a very simplistic way to prove it. The best way would be to find the derivative, right? And make it equal to 0. That's the first derivative test that you do in calculus 1. All right. So actually, I will ask you guys to do that and try. You will get the same answer, 45 degrees. All right, because you will get an equation where cosine equals to 0. The cosine of one angle is 0, 90. 2 theta is equal to 90, theta is equal to 45. So that's another way of proving it, right? So everything that I just did on the board should cover everything that you see in the slides. Now, please don't get confused with some of the parameters, all right? But all the equations that I just did are proven also in the slides, all right? So maybe you just want to stick with my work here, all right? Let's actually do a problem and then we can go into the particular situation, all right? Yeah, let's give you a problem. It's not gonna be like the way in the slides. So. All right. I'm gonna give you a particle object that is living or being launched with 40 meters per second at an angle of, I'm gonna use 37. I wanna introduce you guys to the 3, 4, 5 triangle to that right now. For the 3, 4, 5 triangle, this is what you need to know. If this angle is 37, this angle is 53. The ratio of the sides are like 4, like 3, like 5. All right? That's another triangle that you can use. So first, I'm going to ask you to find the maximum height. So what's the maximum height this projectile gets at this point? So this H max. We are going, the first step, guys, is that you break into components. 40 cosine 37, and By is 40 sine 37. The cosine 37 is 4 over 5. So that will give you 32. And the sine 37 is 3 over 5. That will give you 24. Gravity is negative 9.8. We know that. On Y, the maximum height on Y, so for the maximum height on Y, the final velocity is 0. So I can use the equation B final on Y squared equals to B initial on Y squared plus or minus 2G H max. And what is that H max? I mean, what is the B initial and B final? Well, we have it. 0 and on Y, 24. So 0 squared is equal to 24 squared minus, because gravity is minus 9.8, H max. To the other side. All right, so now, well, calculator. 29.4 meters. What other thing can I find? That time it's on the air, in the air, sorry. So time in the air, which is equal to the time to go up plus the time to go down, or just twice the time to go up. The time to go up, we just use this. The final on Y, the initial on Y, plus or minus, gravity, time to go up. This is 0, right? So 0 equals to 24 minus 9.8 time to go up. So time to go up is 24 over 9.8. 2.4 seconds. The total time then is 4.8 seconds. So twice that. Right? You can put it here. So the total time equals to 4.8 Let me actually show you something very interesting. Many students get confused about this point. This is the point where the object lands. Guys, the object doesn't land with 0 speed. First of all, because you know this speed is constant. At this point on X, it's still 32. In fact, remember guys, that at the maximum height, we are saying that the initial velocity is 0, but not the X. It's always moving with the same X velocity. So here is 32. What about on Y? Can I find the velocity on Y as it crashes? Yes, you can. When the object is falling down, it will get a V final on Y from this point, which is the maximum height. What is the velocity at the maximum height vertically? Here, dy is 0. Now we're going down. So on the motion going down, so going down, I'm gonna highlight this here, going down, the V initial on Y is now 0 meters per second. That's why I like to divide this into two. These were the initial parameters. These are the initial parameters. Not the final ones though. Well, here it is, but not for Y. So now going down is 0. Gravity is 9.8. We have the maximum height, 29.4. I can use this equation to find the velocity on Y. And then I will, as you expect, the velocity on Y will have some magnitude. The total velocity will be a vector like this. So let's actually use that. So 29.4 is the maximum height, right? So land, it will land with some velocity. I'm gonna call it V final on Y with 32. So the general motion will be something like this. That's the V. Without that. When it lands, like that. So how do we find this? Well, V final on Y is equal to V initial on Y minus, sorry, you cannot use this equation, you don't have time. Well, you do have, but let's use the maximum height. V final on Y squared equals to V initial on Y squared minus 9.8, so 9.8, 2, sorry, plus 2 times 9.8 times 29.4. This is 0. So the final on Y, this one here is the square root of all that. So if I use my calculator, well, it's what you expect. Actually, we got the same. We got 24. Interesting. Yep. So 24, 32, that means that it goes like that with 40 meters per second. That's also because of the symmetry of the problem. How about the angle that we just did, right? This angle theta. Tangent of theta is dy over Vx 24 over 32, and it will give you 37 degrees. So give you 37 degrees. So that's a problem on projectile motion, guys. We're going over the web assign later. Next video we'll do free fall projectile motion. Just to give you a small glimpse of that, it's a simplistic version of this. The free fall projectile motion is as follows. Imagine you are in a roof. So you have a building, or you're on top of a building, and you kick a ball horizontally. It will do this. From certain height h, it will get some range x, and gravity will make it go down, of course. What we know is that this is v on x only. On y, there's no speed. But as it goes down, it gets some speed. So here, or here, or here, the velocity is always v here, v on x, but there is some vy that is slowly incrementing because of gravity. So you only have to worry about one component again. We will do that next video. All right. Hopefully you guys get the best out of these videos, and I will see you guys on the next one.